Okay, we're going to start gas laws, and we did gas laws last year, so a lot of this is going to be review. Properties of gases. Gases always expand to fill the volume of the container that they occupy. They form homogeneous mixtures. They have low densities, they are highly compressible, and they exert a pressure. When I say they form homogeneous mixtures, what that means is in air right now there's some oxygen, there's a lot of nitrogen, there's some carbon dioxide, okay? They're not at different levels because of their densities. They're all mixed together, okay? So if I grab a certain sample of air, it will have nitrogen, oxygen, and carbon dioxide in it. Okay, I don't have just carbon dioxide at the bottom of air and oxygen in the middle and nitrogen at the top of air. It's all mixed together. Pressure is a big part of gas laws. Pressure, volume, and temperature. Volume is going to be measured in liters or milliliters. Temperature is going to be measured in Kelvin. Pressure, which is equal to the force divided by the area from which it's pushing on, has different units that we're going to use. It says pascals here. We're probably going to use ATMs mostly. Millimeters of mercury, I'll show you that in just a second. Torr would be another one. Gas exerts pressure by bouncing off surfaces, collisions with the containers. I mentioned that in the other video. Gas particles are evenly distributed in a container. The same numbers smash off every centimeter squared per unit of time. Each collision exerts a force. The pressure is constant at constant temperatures. Okay. This is just natural or standard pressure pushing on you. You're so used to it that you don't normally feel it anymore. But if I doubled this pressure, you would definitely feel it. So if I have a container and I hook it up to a vacuum, but I don't turn the vacuum on yet, this is atmospheric pressure pushing in on the container. This is the gas that's inside the container pushing on the opposite. Okay, the pressure inside equals the pressure outside. However, if I turn the vacuum pump on, I'm going to be taking the gas molecules out. If you'll remember that scenario that I showed you earlier, the simulator, I'd be taking the blue balls out. If I take the blue balls out, then there's less air inside colliding with the container. Therefore, now look what happens. I have a higher pressure outside than I do inside, and it crushes the can. Barometers are one way that we can measure the barometric pressure. So atmospheric pressure for the day pushes down on this big pool of mercury, and atmospheric pressure pushes on the mercury, and the mercury rises. Hopefully you've heard of that before. You can then measure the distance that the mercury rises, and on an average day it's around 760 millimeters of mercury. Sometimes they measure it in inches. If you watch the news, the weather, they measure it in inches of mercury. Remember, there's three different types of movement for all molecules: translational, rotational, and vibrational. Most of the kinetic energy for gases comes just from translational energy. Just like you saw in the simulator, they bounce back and forth. They have collisions experienced by gas particles that are elastic. Kinetic energy is always conserved when they collide. Okay, one might be going slow, one might be going fast, and then all of a sudden the other one goes slow, and this guy turns and goes fast. But there's no kinetic energy lost. Also, kinetic energy is always going to be the same if you're under the same conditions. Whether I have neon, helium, or argon, they're all going to have the same kinetic energy if it's the same temperature and the same volume and the same pressure. Okay, Boyle's law. Volume and pressure are inversely proportional. That means when one goes up, the other one goes down. So V1 P1 equals V2 P2. And we looked at this earlier. If I decrease the volume, there's more collisions with the container, therefore the pressure goes up. If I decrease the volume in half, then that means that the pressure would double. Charles' law is the relationship between temperature and volume. And remember, if I increase the temperature, the molecules are going to move faster. If they're moving faster, there's more collisions with the container. If the container is allowed to expand, it will. If you decrease the temperature, there's less collisions with the container because they're moving slower, and therefore the container will contract. Don't forget, temperature has to be in Kelvin. So we've got V1 over T1 equals V2 over T2. And that is a direct relationship, so that's what the graph would look like. The combined gas law is when I take all three. They didn't mention the P1 over T1 equals P2 over T2, which is Gay-Lussac. But if you combine all of them, this is the combined gas law. V1 P1 over T1 equals V2 P2 over T2. So, a cylinder of gas is kept at a constant volume as the temperature increases from 24.1 to 326.4. If the initial pressure is 1.10, what is the final pressure in millimeters of mercury? We're going to do V1 P1 over T1 equals V2 P2 over T2. Notice that the volume remained constant in this problem, so I'm just going to cancel that out. Plug in my 1.01, plug in my temperature in Kelvin, plug in my temperature too, solve, and I get a pressure of 2.04 atms. But that's in atms. I want millimeters of mercury. So 1 atm is 760 millimeters of mercury. The answer is 1.55 times 10 to the third. Avogadro's principle says that equal volumes of different gases at the same temperature and pressure contain the equal number of particles. So if I have 4 balloons that are the exact same volume, 1.5, 1.5, 1.5, and 1.5, each one of these balloons, even though it has different gases in it, will contain the same number of particles. Don't forget what STP stands for. STP is standard temperature and pressure. Standard temperature will be 0 degrees Celsius, which is 273 Kelvin. Standard pressure 1 atm or 760 millimeters of mercury or 760 torr or 101.3 kilopascals. Remember, these are not the same standard conditions that they were in thermo. Also, don't forget that at standard temperature and pressure, 1 mole of any gas is 22.4 liters. 1 mole of helium, 22.4. It's also 1 mole, 6.02 times 10 to the 23rd gas particles. The ideal gas equation, PERVNERT, PV equals nRT. So I've got pressure, volume, temperature. N is now the number of moles of gas, and R is our ideal gas constant, 0.0821 atmosphere liters per mole Kelvin. An 8.5 liter tank contains helium gas at 16.9 atms and 25 degrees Celsius. How many moles of helium are available for making balloons? Well, I've got volume, I've got pressure, I've got temperature, so I can solve for the number of moles. I get 5.9 moles of helium. If all the helium is used to fill a 1.5 liter red balloons at 0.99 atm and 32 degrees Celsius, how many balloons will you end up with? Well, volume is what we're going to be solving for. You get 149 liters. Plug in your moles, plug in the temperature, plug in the pressure, and you get 149 liters. If one balloon is 1.5 liters, then we have 99 red balloons. That's a song from the 80s. Okay, an unknown gas is collected in an 850 milliliter vessel at 1.0 atm and 23 degrees Celsius. The evacuated vessel has a mass of 138.45 grams. And the vessel and the gas together have a combined mass of 140. So if I take the container with the gas, subtract the mass of the container, I'll get the mass of the gas. Find the molar mass of the gas. Well, I've got pressure, I've got volume, I've got temperature. Plug all those in, solve for the number of moles. Now that I have moles, remember, molar mass is always grams per mole. So I'm going to find out what my grams are divided by my number of moles. So there's my mass divided by my moles, 46.8 grams per mole. An unknown gas that is a hydrocarbon has a density of 3.24 grams per liter at 1 atm and 28 degrees Celsius. Find its molar mass. All right, here we go. PV equals nRT. I just told you that mass divided by molar mass is number of moles, right? Grams divided by moles, molar mass is number of moles. So if I take this equation and rearrange it, put molar mass over here, take PV and put it down here, molar mass is equal to mass RT over PV. Well, remember, mass over V is density. which I do not use that symbol for density, but you guys can still see it. So if I'm trying to solve for the molar mass, it's going to be density RT over P, or what I like to call dirty P. Cats always put dirt over their P. An unknown gaseous hydrocarbon has a density, once again, of 3.24 grams. That's going to go here. Pressure of 1. R is 0.0821. Plug in my temperature, and I can solve for molar mass. I get 80. What volume of carbon dioxide gas can be produced when 68 grams of methanol burns in air at 25 degrees Celsius and 1.02 atm? So now we're going to do stoichiometry with gas laws. Okay, I'm looking for volume of CO2, but I have 68 grams of methanol. So I'm going to go grams to moles, mole to mole ratio, and then I'll have my moles of my gas. Once I have my moles of my gas, temperature of my gas, pressure of my gas, I can solve for volume of my gas. So grams to moles, for every 1 mole, for every 2 moles of methanol, there's 2 moles of CO2. And 2.1 moles of CO2 is what I get. So that will be my N, my number of moles, temperature, pressure, solve for volume. 2.1, that's my number of moles, 0.0821, temperature divided by pressure, 50 liters of CO2.